Before I get started, I'd just like to thank the organizers, because it's been a great meeting, both mathematically and technologically, that everything has worked extremely well. And I hope everybody can see and hear well, because that's what I found was very good for me at this meeting, that I could see and hear very well what everybody was saying. And I hope to be able to, that you will have a similar experience. So I'm going to try and connect some things to topological recursion. So there's going to be three parts to my talk. So the first is infinitesimal freeness, which was something introduced by Belinsky and Shlekhtenko about 12 years ago. There's the orthogonal Weingarten calculus from the 2006 paper of Collins and Sniady. And then I'm putting these together in something which I am whimsically calling infinitesimal Weingarten calculus. So I'm stretching the words a little bit. I just tried to make a catchy title so you would listen to the talk. So first thing I want to talk about is infinitesimal distributions. And this is nothing particularly new, but there was a paper written by Shlekhtenko in 2018, which showed that some of the ideas of infinitesimal freeness could be applied to analyzing what some people in random matrix theory called spike models. And that's where you take a random matrix and add a fixed finite rank perturbation to it. And as the size of the random matrix goes to infinity, the contribution of that fixed thing is getting very small, but it can still be measured. And the idea was to find a way to model it mathematically, and it was found that infinitesimal freeness could model this. And that was what was in this paper of Dima Shlekhtenko from 3 years ago. So let me just give you a couple of examples of what I mean by an infinitesimal distribution. So we'll just start with our favorite matrix, the Gaussian orthogonal ensemble. So it's important here we use the orthogonal one and not the unitary one, because the infinitesimal law for the unitary one is 0. So it's not very interesting. And we let Mn be our limiting nth moment. Which we know we can write as an integral against the semicircle law. And it's also, and this is important, the number of non-crossing pairings of n elements. So I'm taking that to be 0 if n is not even. Okay, and then there's this idea of an infinitesimal moment. So you look at the way at which the this thing approaches its limit, and you take a derivative. So and that means you take the limit and you multiply the difference by n. And you can prove that that limit exists, and it is also given by the integral against a measure, but it's not a probability measure anymore, it's a signed measure. So it's going to be the difference of two probability measures. So the first one is a symmetric Bernoulli distribution with variance 2. And the other one is the arcsine law with variance 2. Okay, and I'll explain what this means later on. These moments, these are infinitesimal moments, so they're not the moments of a probability measure, but they are moments of a signed measure, are counted also by some combinatorial objects, which I'll explain later. What that is, but they are planar. That's the thing that some of you saw me talk about this a few years ago when I noticed that these things are also counted by planar objects, but they're annular drawings on an annulus, but they're planar and the genus is 0. In some of the earlier literature on these things, this is the subleading term of the genus expansion of the GOE. You can also describe them as maps on non-orientable surfaces, but here I'm looking at orientable surfaces. So by going to an annulus, I guess you could think of it as some kind of double cover, you get rid of the non-orientability. Okay, what's in one other little example? So we take a real Wishart. So G is Wishart random matrix. So Gij are IID real N01 Gaussian random variables. Okay, and of course we can do the same thing, and we get the Marchenko-Pasteur law. And we have to assume that there's a parameter that the aspect ratio, yes, I didn't say what this is. This is an M by N matrix, forgot that. And we have to assume that M over N actually converges to some parameter C. So we get the Marchenko-Pasteur law of parameter C. And you can again look at this infinitesimal thing to see if there's a limit here. And let me just write it down. Yeah, you get two terms. The first one, I'm going to write it a combinatorial picture. Sorry, that's not what I meant to write. So let me just finish writing this out, and then I'll try and explain what this means. Okay, so let me just go back up here to the Marchenko-Pasteur law. This also can be written and using free cumulants. So I'm taking the non-crossing partitions on n elements, and this exponent is the number of blocks. And I say that this is another way of saying that kappa n is C for all n. So the Marchenko-Pasteur law has particularly simple free cumulants. They're just all equal to C. Okay, and that means the moment, which is using the sum of cumulants, is just C for each non-crossing partition is just C to the number of blocks. This part of the formula was found by Andrew Nika and myself about 20 years ago when we were looking at annular non-crossing permutations. And we didn't really know what the formula meant, but we just noticed that we could compute it, and I didn't say what C primed is. C primed is the limit where you take n times m over n minus C. And sorry, that's the wrong n. So in both of these setups, you have to assume that this limit exists, and you have to assume that that limit exists. So I mean, in principle, those limits don't have to exist because you don't know what m and n are. So what this does look like, and what we noticed back then, is that it looks like differentiation. You differentiate implicitly this expression with respect to some implicit parameter. You get this where C is the derivative. Okay. So in our paper in 2003 or whatever it was, this term wasn't there because we were looking at the complex Wishart distribution. And now if you throw in the real Wishart distribution, you get one more term. And I haven't said what this is either. So this is very similar to this other thing up here, which I said will be explained later. Okay. So let me just say a little bit about infinitesimal freeness. So this is from a paper of Belinsky and Shlaktenko. I think it's 2009. 12, sorry. Okay, and so this isn't exactly how they put it, and I'm just going to give you a version which was found recently by a Queen's student, Palon Singh. So the idea is this: you start with a non-commutative probability space A phi, but you have an additional linear functional. So you have phi going from A to C, and you have phi primed going from A to C, and they're linear. And phi of 1 is 1, so that's our usual state that we always have in free probability. It's like the expectation of the normalized trace. And phi primed is just some other linear functional, but we require that it kills the constants. We're supposed to be thinking of a differentiation. And in the original formulation of Belinsky and Shlaktenko, they used an idea of type B freeness. But there's a way that you can avoid that, and that's what Palon Singh found. So let me just show you what he did. So you use an idea from non-commutative functions. You use these upper triangular matrices. So you make you just look at upper triangular matrices where the two diagonal entries are the same. Okay, and then you can do this to the complex numbers. Okay. And you get a two-dimensional commutative algebra. And then you make a linear functional doing the same thing. You make a matrix of linear functionals, and this goes from, okay, and now if you take two subalgebras, which are unital, you say they're infinitesimally free if A1 tilde, A2 tilde are ordinarily free with respect to phi tilde. So you can just reduce all questions about freeness. As far as I know, everything you want to do about infinitesimal freeness can go through these things. You can do the R transform, the S transform, the Voigt-Kolasky, all those things go over. In fact, this hasn't been explored too much, but there is one paper of Maxime Féray where you don't stop after the 2x2 matrices. You can go as many as you want. You just do nilpotent matrices in general. And you get higher infinitesimal freeness as opposed to higher order freeness. So it's, the terminology is a little complicated, but I'm going to leave that there. That just shows you what, I mean, where these infinitesimal laws come in. So there are rules for doing the free convolution of infinitesimal laws. Yeah, okay, now I think I forgot to say something. If you go back here, we have these two measures. We have mu and mu primed. And that's what we mean by an infinitesimal law. And here, you can also write down a pair of measures. This one is going to be a semicircle law. And this one, there's one law for this term, and there's another law for this term. So you get a similar thing where you get a difference of signed measures. So I don't know if there's a general theory, but you have two examples where the infinitesimal law is it's a difference of two probability measures. And for some reason, there's a 1/2 in front of it, but that just seems to be the way it goes. Okay, so I don't have too much time left. So now I want to talk about the connection to the Weingarten calculus. Okay, and so what I'm going to tell you is from this paper of 2006 of Collins and Sniady. Okay, so this is a way of computing some matrix integrals. So let me just remind you what the setup is. So I'm going to start with n by n orthogonal matrix. And the problem is to compute with respect to Haar measure a product of entries. Okay, now I'm doing something that's probably a little weird here is I'm putting negative. So this is O sub I n and then I minus n. It turns out that's a convenient way to write this. It looks a bit unusual to do this, but I hope I'll convince you that at least that part is Okay, and what Collins and Sniady showed is that, okay, this is, you could almost say this is a definition, but let me just write it like this anyway. Okay, so you can completely integrate out the Haar measure and reduce it to a sum over pairings. So let me just explain the notation here. All partitions of the integers 1 up to n with blocks of size 2. Of course, this will be an empty set if n is an odd number, but so that's implicit here that n is even. And now, here's another thing that's very useful in this business. So if you start with a pairing, you can think of the pairing as a permutation where each block of size 2 is a transposition. Okay, then you can do another thing. This is that everybody does this. Here's something that not everybody would like. I'm going to embed Sn in the permutations on the integers 1 up to n and -1 up to -n. Right, so I'm going to, maybe I'll use this notation. You take 1 - 1, 2 - 2 up to n - n. Exactly the numbers that occur in the subscripts of these indices. Okay, and now you do this by saying that if I take a pi here, I know what it does to the positive numbers. It just does what pi already did, but on a negative number, it's going to act trivially. So this is like how you embed Sn into Sn plus 1. You let it act trivially on the things that come after. So you do the same thing here. And then finally, you introduce one more permutation, which is kind of the key to the whole thing. It's the permutation that changes the sign of every number. Okay, and so now, what is this thing down here? That is the product of those 4 permutations. So it says you do P on the positive numbers and Q on the negative numbers. And this thing here, I can now tell you what this means. So I'm going to have P delta Q delta. And this only takes on 2 values, either 1 or 0, and it's 1 if I is invariant under this permutation, and it's 0 if I is not. So remember, this is a permutation of the domain of this function I. So we're asking that if you precompose I with this permutation, it doesn't change the value. Okay. And then the last piece is I have to tell you what this thing is. And of course, that's the subject of the whole talk. That's the Weingarten function. So let me just tell you what that is. So you do the following thing. You make a vector space by taking the pairings as a basis. And then you make them an orthonormal basis, give it an inner product. So we say that the inner product of P and Q is 1, P equals Q, 0, P not equal to Q. So we make it into a Hilbert space, and we define a mapping. Let's call it G. From this space to itself. Now I'm going to try something here. I think there's a way I can insert a page right here. After. Yes. Okay. Great. Okay. So we can yeah. And how did we define G? G of P inner product Q is going to be N, the size of our matrix, to the number of blocks in P sup Q. So P and Q are partitions. The sup is the smallest partition that's greater than or equal to both of them. So this won't be a pairing anymore in general. But it is a partition, and we count the number of blocks and we raise n to that power. And if the big N is bigger than or equal to little n, G is invertible as an operator on this Hilbert space. And we let WG be the inverse. Okay, and if you just look at this matrix, the matrix of G, it's all, the entries are all n to some power. So when you compute the inverse, you're going to get rational functions of n. So W, yeah, I'm going to also introduce a little bit of notation. Let me back up. I'll say that WG PQ, which is just shorthand for this thing, is a rational function of n. Now, it turns out finding explicit rules for this is pretty complicated, but a lot of work has been done. But the way a lot of people have approached this, although is to expand it as a power series in 1 over n. Okay, and so I'm just going to say that WG P comma Q is going to be the leading term, which I'm going to call W1 of PQ. And we know what order that is. And then I'm going to call it W1 primed of P comma Q. And yeah, maybe I'm going to call this W2 PQ, although I don't know if that's good notation. So it goes down in steps of 1 each time. And what's the notation here? I actually don't have the benefit of having seen Roland's talk this morning because it wasn't on YouTube when I checked. So he may have defined this already, but I'm just going to assume that he hasn't. If I have any partition, I let the length of that partition be n minus the number of blocks, just like you do with permutations to put a length function on permutations. Okay, and so that's the expansion. One thing that's very, very important for free probability theory is this is a product of signed and shifted Catalan numbers. So that's in that 2006 paper of Benoit and Piotr. Okay, so let me just tell you how that goes. So this is an important part of everything else I'm going to say. So it's worth doing this. So what you do is this. You take your pairings, and now you think of them as permutations, and then you multiply them. And you decompose it into a product of cycles. and the number of cycles is always even. In addition, the cycles always occur in pairs. And you can't tell which one is Ci and which one is Ci primed, but they all satisfy that little relation. You reverse the order of the entries and conjugate by Q. So I call these conjugate. Okay. Right, and so now what's the formula? On W1 of P comma Q, I said it's a product of signed Catalan numbers, so I'm just going to call them mu L1 up to mu Lk, where Li is equal to the number of items, well, the number of, yeah, let's call them items. I don't know if that's the right word, but in the cycle Ci. So if Ci has 5 things, then Li is equal to 5, and Ui is this signed and shifted Catalan number. So it's -1 to the I minus 1, C sub I minus 1. Yeah, maybe that using I twice, is a bad idea. And I'm going to call this L. Okay, so that means that the leading order of the Weingarten function is just this product, and that's turned out to be very important in free probability theory. So this means that for unitarily invariant or orthogonally invariant ensembles, you can get a lot of mileage out of knowing how to compute this. Okay, and let me add another page. Okay, good. So that's the leading order. And now it was a question for a while. What can you say about the subleading order? So I'm kind of giving the game away here by putting this primed on it, that somehow it's connected to infinitesimal distributions. So I didn't find this. This was found by Valentin Féray about 10 years ago. So, just to give a little of history, there was a paper of Matsumoto where he wrote down a conjectured formula for this. And then about a year later, Féray proved that conjecture. And so there's an explicit formula for it. You do the following thing. You take, you're going to take this formula right here and differentiate it. So you're going to take R goes from 1 up to K. That's how many factors you had. And you're going to differentiate them one at a time. Mu L1 to mu LR primed, mu LK. So you're just going to use the Leibniz rule. You take a product and you differentiate it, and now you have to say what one of these things is. So we know what mu L is. What is mu L primed? That's what Féray found in his paper, and there's a formula. It's -1 to the L. It's 4 to the L minus 1 minus 2L minus 1, choose L. In addition, he also, so he found this, and then he related it to something involving the area under Dick paths, and he found another paper from 1992 which found a recurrence formula for the area under Dick paths. So let me write that down. So I take L goes from 1 up to m minus 1. And now I have the product mu L prime times mu m minus L plus mu L mu primed m minus L. So this is a kind of recursion formula that if you know the mu's, okay, so you know the mu's from here, they're the signed and shifted Catalan numbers, then you can inductively compute these ones because you only go up this far in the sum. So there's a kind of recursion here for computing these things. And then you stick them together using this Leibniz rule. Okay, so what's my contribution to the subject? Okay, is I found an interpretation of this in terms of planar diagrams. Yeah, oops, sorry, I got this switching colors here. Anyway, the signs actually are just an annoyance because in this term here on the right-hand side, everything has the same sign. So there's no cancellation. So the signs are kind of a red herring. But so what's the formula? It's a certain counts the number of diagrams of a certain kind. And the point is that these diagrams can lead you directly to this recurrence formula in the same way that we just saw in Bertrand's talk, that you do cutting of the diagrams open, and you can then reduce it just by going down by one. So that's what I'm going to tell you about in the last 10 minutes. Okay, good. So it's time for this. Okay. So let's look at this picture. So I think, I hope Roland explained what a non-crossing annular permutation was. So you have two circles, 4 points on one circle, 3 points on the other circle in this case. And you make blocks that connect the points, but it has to be done in a planar way. So genus 0. And they have to be oriented so that they all go the same way. So in this particular picture here, the blocks, you're always going around this way. So if you draw it on an annulus, okay, they go the other way, but here I've reversed everything. Okay, and it's important that you count permutations and not partitions, because sometimes if there's two ways of going around it, you want to count them differently. So those are the non-crossing annular permutations. Now, the thing that comes up with the GOE, with the real Wishart, and there's also a real version of Keston-Mackay law where all these things come up in the same way. So I think, yes, and I know there's also an application that Octavio Arizmendi found involving Laguerre polynomials. So I would say these diagrams have now shown up in 4 places. So I think we can say it's a thing. Now, okay, but what's the other one? What's the new thing? Okay, you take the number. So I'm going to notice there's a 4 and a -4 here. So I'm just being a little whimsical with the notation. You put the numbers 1, 2, 3, 4 around one circle, and -1, -2, -3, -4 around the other circle. Whoops, you go this way on one of them and you go that way on the other one. And I put a minus sign here because in this picture, the circles are oriented in the same way. So it's 5, 6, 7, 1, 2, 3, 4, but now I reverse it. Okay, and delta, this delta up here means that there's an additional symmetry. The additional symmetry, we can write it as a couple of ways. Let me just see. Yeah, so let me write down the exact statement. So So you could, all of these things can be written in terms of the symmetric group. So all the calculations I ever do are always in the symmetric group. You draw the picture to inspire you, but then you compute in the symmetric group. And they're defined by a geodesic condition. And a connectivity condition. And I have to say what gamma is. It's a permutation with 2 cycles. And this condition here says at least one cycle of sigma meets both cycles of gamma. And so this set is, I mean, the topological condition is given by this geodesic thing here. Let me get another page. Okay, so that's the set of non-crossing annular permutations. And then what is this new set? Well, it's quite easy to define now. So we say SNC delta n minus n. Okay, it's the set of things in SNC n minus n. I guess I didn't say what that is, but I'll get to that in a second. Sorry, I didn't leave room. Oops. It's just a way of drawing it. There we go. So by this minus n here, I just mean you put the numbers on the other circle going in the opposite order. And delta is that permutation that flips the sign of every number. And so the condition is just that sigma delta is a pairing. Or another way of doing it is to say that delta, conjugation by delta permutes the cycles of sigma, and you get an involution of order 2 without a fixed point. So every cycle of sigma has to go to another one. You can see exactly in this case, I take this cycle here, and when it's 1, 2, -4, and -3, and when I flip the signs, I get -1, -2, 4, and 3. And so it gets mapped over to that one. So this one is particularly obvious. I think I've got, yeah, here's some more pictures over here. So here's a case where you have 2 blocks of size 5. And yeah, I mean, now I'm just going to show you how to these things. It turns out you can parameterize them quite easily. So I didn't wear my t-shirt or the kind that Roland had. I do have one, but there's a way. I mean, this is where that picture comes in handy. Anytime you have a permutation, you always turn it into a pairing, and you can do it in the symmetric group. And I'm just going to show you geometrically. You split all the points. Okay, there's just a canonical way of splitting every point. And then when you do this, you see that the diagram has an inside-outside symmetry. If you know the inside diagram, you know the outside diagram. So you really only worry about the inside diagram. And so here I've sort of turned it upside down, or I've flipped the outside diagram on its head. But these 2 blocks here are the through blocks. Right, so I'm really just sort of cutting the thing off like this. And I can completely parameterize this thing by saying where I put these black dots, which are written in white, because remember, this is a blackboard. And So I have 3 black dots on primed elements and none on unprimed elements. And there's a formula here. You just, you say it's the sum over all B and B prime greater than or equal to 0, n choose B, n choose B primed, such that B plus B primed minus subtracted from n is even. Okay, so there's a complete description of these diagrams. So let me try and connect in the last 2 minutes to topological recursion. Okay, so here's a formula from a paper of Benoit, Piotr, Roland, and me from 2007 in the unitary case, where we looked at something called the Möbius function. Möbius function is just the leading order of the unitary Weingarten function. And there's a recursion, which just goes exactly like what, using the same idea that Bertrand showed us an hour or so ago, that you can cut your disks. I mean, this is the case when you only have 2 boundaries. You can, I mean, you can compute these things as these are signed, and this is sort of like, or this is regular what you get in the orthogonal case, and this is what you got in the unitary case. In the orthogonal case, we had this thing. Now I'm going to just jump ahead a picture or 2. Yeah, okay. So I'm just trying and explain how you do that. Here's that formula down at the bottom. So there's, there's 2 things on the right-hand side here. There's something involving 1 boundary. That's just a regular signed and shifted Catalan number. And the idea is you look in the Quervaras complement and you see what 1 is connected to. In this case, 1 is connected to -4. So you're really just doing a non-crossing partition on this thing. If a 1 is connected to something on the same boundary, then you've split this into 2 parts. You've got a non-crossing partition on 1 point here, and now you've got, on this side of the line, you've got a something with 1 fewer point. Now this thing is in there, but it's already taken count by symmetry, so we just kind of ignore that. And so there's the topological explanation of this formula. Now I see there's just 1 minute left. Could someone ask, well, what happens if you go up to the next term in the expansion?
James?
Oh, yes. Yep.
We started about 10 minutes late, so you have quite a bit of time if you want.
Oh, okay. Oh, that's okay. I'm nearly done, so everybody can get to their dinner on time. But let me just say, what happens if you go to the next term? Well, you can, yeah, so here I just did the case. Yeah, so let me just go back to this expansion here. Maybe it'll be a little clearer. Okay, so let's look at this formula here. So I only had 1 primed. Now you do it again, you can do 2 primes. So you might prime the same, you might prime different elements, or you might tame the second derivative of something. When you differentiate something twice, you get 1 second derivative, which looks like a regular non-crossing annular one, and then you have the mirror image on the conjugate side. And so there's a kind of a symmetry like that to the conjugate pair. Or you could have 2 first order derivatives. You could have 2 of the cycles that have this annular one. And so you have 1, 2, 3, 4 on here. And look, I have another one going the other way inside. And then I have something like, so you can have 2 first derivatives or 1 second derivative. So I don't want to say that's a theorem yet because I haven't checked everything, but it looks like you can also push this idea a little further to get more recursions. Yes, I forgot I meant to put this in my slides, but if you go way back to this thing I did at the very beginning, for the GOE, there is a formula for the genus expansion. of the GOE, like the Hauer-Sagier one for the GUE, but it's way more complicated. I don't know if anybody's mentioned it. I haven't seen it mentioned in the conference so far, but it's a much more complicated formula. So what I'm hoping is these planar diagrams can make some of these things more transparent. Okay, I think that's all I plan to say. So stop and ask for questions.
Okay, are there any questions?
Maybe I'll turn off my screen so if somebody, I can see the part of the room anyway.
There's a question back there. Just give me a second to bring the microphone.
Okay.
Okay, this is Octavio. I don't know, you see me.
Hi, Octavio. Yeah.
So I have maybe two comments. Maybe one comment is, I think, what happens when C prime is 0 and C equals 1?
Yeah, okay. Let me go back to my screen. Yeah. Second, it always takes a bit. Okay. Yeah, so when C equals 1, then you get, yeah, of course, C primed is 0. So, I mean, remember, C prime tells you how this aspect ratio approaches C. So if you use the continued fraction expansion of C to use those to get convergence, C prime will be 0. But you can choose other C's. So this could easily be 0. When C equals 1, then you get exactly Mn primed. Maybe I'll just put that here. This is exactly -1 to the n times mu n primed. So mu n primed is either positive or negative. So I have to put a -1 to the end to make it a positive. That will guarantee that it's a positive integer. Was that your question?
Yeah. I just wanted to point out that this is the same numbers. I think you didn't mention that these are the same numbers that you get for the Weingarten formula.
That's right. Same number. Exactly. Yeah. Because here we're counting. I mean, I know how to. I mean, that this guy actually just counts that set. Okay. So when you put C equals 1, it just counts the set. Yeah.
Yeah. Okay. And maybe
that's right. Thank you.
Another question. Do you think one can get with this Grassmannian or this matrix? One can do like a second order infinitesimal freeness or something like this?
Possibly. I mean, I should just tell you a little bit how I found these things. So, I mean, in the Collins and Sniady paper, they wrote a sum over all pairings. And when the points is small, you can't really see anything. So you got to have at least 4, 6 points. But then the number of pairings is pretty big. So I just asked the computer to find all the pairings that give the right terms, and I just figured out a way of drawing them. And I completely forgot about it. Let me just tell you where the pictures. I mean, how do you go from a pair of pairings? Yeah, sorry, I completely forgot. But okay, here's the idea. So we take 2 pairings. And now I'm going to do the following thing. I'm going to assume that there's only that, no, sorry, I don't want to do that. Let me just take it back. Okay, sorry, I just multiply them. Okay, so, and I decompose into cycles. Right, so, I mean, the way I did this is I always assumed that Q was, yes, yeah, let me see, I'm maybe I didn't prepare this, so now you caught me flat-footed, but anyway, I'll try and make it up as I go along. So the idea is that n is 2m, and I'm going to write this set n from 1 to n as 1 up to m and -1 up to -m. And I'm going to take q to be this particular pairing, and then I decompose this the cycles and I get one of those diagrams. Now, the reason that's legitimate is that the Weingarten function is central. So one pairing is the same as any other pairing, right? Because you can always conjugate one pairing to another pairing if you're only evaluating the Weingarten. So you always assume that Q is one particular one, and let P run over the whole set. And then you just go and find all the P's that give the right order. So that's how I got these pictures down here for second order things. Sorry, let me just, for these things, as I just ran the computer and found some things. So I think the way to do this is you turn on your computer and try and ask it to add this up and then look in the tables. So there's tables first written by Piotr and Benoit, and then Benoit and Sho Matsumoto on these orthogonal Weingarten functions, and see if the numbers match the tables. And when they do, you know you found them. And then now you just have to figure out what the statement is. But that's what I would do.